from the beginning. Okay.
Yeah.
So we chose problem C, and our project is studying the relationship between density of human population at a location and the loss of anti-predator traits in the prey animals. Generally, we assume that preys are evenly distributed in a plane initially, and human move in and diffuse throughout that plane. Also, we use Weibull distribution to model the assumption that preys lose anti-predator traits based on the extent of contacting with human and the duration under human contact. And then we track the changes in anti-predator traits based on density of human at each given point. In the rest of the presentation, we'll denote the bibliography of problem C to the paper. In our model, we consider a square bounded by the 2 points, and time ranges from 0th to the 10th generation. We modeled the movement of a human population throughout this plane using the advection diffusion equation. And then we define a relationship between the density of human population at a point and the loss of anti-predator traits, which we use the Weibull distribution for this relationship. And then we use this information in a modified predator-prey model. And this is our variable table. We have XY denoted to the position in a plane, and T for the time, which is the generations, and U using the variables XYT denoting to the function given the population density at a position X at time T. The anti-predator response is the function using the variables X, Y, T, and G to represent the mean anti-predator response of an animal of gregariousness G at position X at the time T. And G is the gregariousness factor from 0 to 1, which 1 is the most gregarious and 0 the most solitary.
This is how we got our idea with changing the Weibull curve from the as a relationship between the gregarious factor. We use this finding in a paper where it shows that gregarious animals have like this light green curve in terms of anti-predator response in human presence, and solitary animals have this deeper green curves. So we use Weibull curves because we found that it has a similar shape, and then using Y as like the gregarious factor, we use this as like a variable that we could fit in as an extra parameter in the Weibull curve and obtain like a curve for a response. So right now we're trying to solve the human movement equation. So here, this is our equation. We use like a mixture of, advection diffusion equations on a human movement. And so we set the diffusion coefficients on both directions to be 0.5. And then for the advection equations, we set it to be like a piecewise function, so that when t is less than 4, it's 0.8, but when t is greater than or equal to 4, is 0. This gives the effect of so like after time t equals 4, the advection stops. So the only movement of the humans are just like kind of like from the middle. The humans will start diffusing from the middle. And then after we have solved this, we use the set of solutions U of XYT into this anti-predator trace function, which takes in the X position, Y position, time, and gregarious factor as input, which, although it looks complicated, it basically says that the decrease in anti-predator traits only starts after a human presence has surpassed a certain level. Here's the in-depth explanation of the choices that we made in making the anti-predator traits function. We want the animals anti-predator traits to decrease only after the human presence has surpassed like a given level. And so to account for this, we created like a cutoff function that ranges from 0 to 1, and it goes to 1 at about 0.15, which is the threshold that we have chosen. And so here we assume that the anti-predator trait starts at 1, and the Weibull distribution is this big expression down here, and we parameterize it as like the cutoff function's values goes from 0 to 1. And this Weibull function is basically the one that we showed above, where it takes in a parameter g and it slightly changes. And this is the value that we are fitting it into, which is time times the human density. So this is taken into extra account density level of a certain point or area that we're evaluating. Okay, so this is the solution that we found for human movement. Okay, next slide. And so for the anti-predator traits function, we assume that we put this finding from the paper that suggests that human diffusion relaxes the predator pressure for prey. So we take that to mean that humans sort of drive predators out. And so we use this information to so that this informs our decision to make the death rate coefficient in the predator prey model as a function of human density, and also increases the coefficient governing the loss between interactions between prey and predator.
All right, so then this is basically our plane, but now instead of the human population spreading through, we see kind of the drop in anti-predator traits spreading throughout our plane. So it does very much look like an inverse of where the human population is, which is what we would expect. So it kind of diffuses out as this bowl shape. And then using those found values of like the anti-predator mean strength at each location, we plug that into a Lotka-Volterra model as basically the like as how resistant they are to predators. So like our beta constant, you can see what would be a constant in Lotka-Volterra is no longer constant. It changes at each time step based on the strength of the anti-predator trait. So if it's, the anti-predator trait is very weak, then more predators will kill the prey, is the idea. And then the other aspect, which changes over time, is the predator death rate, which depends on the number of humans in that area. So this is one graph of the predator-prey relationship. There would be a similar graph at every single point along our plane. So this is at somewhere in the center. And then here's one on the far edge at 9,9 away. So that's one of the furthest points that it takes to reach because our plane was only 10 by 10. And then one of the early points, 1,1, right where they start, we can see that the number of predators starts out a little bit lower because there are humans there, which means more predators are dying off by the existence of humans. And then once the humans kind of advect away from that location, the number of predators rises back up, and then we have slightly fewer prey than we would otherwise. All right. So as far as conclusions that we have drawn from our model, we found that our model is fairly optimistic. prey animals have a very strong ability to recover their population after humans leave an area. They might just be slightly dampened, the predators rise back up, but it's really they were almost always they were able to recover. And then some further extensions based on this model that we might take were to explore different ways that a human population might spread throughout an area. So just kind of changing that initial like advection diffusion assumption to maybe some other function of spreading throughout. And then one other further direction was to pin down more specific individual mechanisms through which prey animals lose and regain their predator traits. So since we have like this very nice spatial model, it might be good to consider like the movement of prey animals with different strengths of traits to different areas and how that affects the mean, so that they could maybe diffuse and that could help them regain their predator response. But yeah, no, overall we found a fairly optimistic conclusion. But
That's it?
yeah, I guess so.
Okay, great. Thanks. Thank you for watching. Have a good day. Bye.